Hello and welcome back to Calculus2. So we are going to talk about a number of things today. We're going to work with series first, and then we'll have part one of our exam review. So we still have time. The exam will be available on Friday, Saturday, maybe even Sunday. I can toss in. Not sure if you guys need all that time or not, but I can toss in Sunday. It's not a big deal. The idea is to have the exam this weekend so that you can focus on chapters 10 and 11. A little bit of panic mode here because a semester ends in 3 weeks actually. So we'll have to get through chapters 10, 11, and 12. Each one has 3 or 4 sections left. So chapter 12 has 3, chapter 11 has 4 sections, and we still have 4 or 5 sections to cover, 4 sections to cover here. So it's not that much, but when you take a look at the amount of time left and the fact that there is a third exam and so on, so we don't want to rush. They did not add extra week. I was hoping for extra week, but they did not add that back. So we'll have to work with what we have. And remember, this course is very important for your differential equations. So I will have a brief exam review at the end of this class today, and then we'll have a full review on Thursday, and your exam follows the Friday, Saturday, and possibly even Sunday. So you can take all of these. So I'm hoping, if you have any questions, put them in the chat, obviously. But then we can also meet using Microsoft Teams for office hours and so on. Just please look at the announcements on Canvas. So let's talk divergence test and all of this stuff first to get rid of the new material, and then we can focus on the exam. So we talked about power series. I hope that you are keeping current with the new material. You are not just looking at the old stuff that it's on exam, because this chapter 10 is a little bit different than what you used to. We don't have continuous functions anymore, and that's something that it's different, right? So last class we talked about the fact that you either know geometric series or you don't, right? Which means you have to memorize the test itself, the statement of the test and what it means, so the way it works. And we said that R is either between -1 and 1 for convergence or outside of -1 and 1 for divergence. And telescoping series either added to a finite number or added to infinity. Again, convergence, divergence. So now we have the same situation here. You have to learn these 3 tests. Divergence test is the first one we work on, and this is the first test you always check, right? Because it spots divergence instantly. It's one limit you take very quickly, and you should try this first for every problem you ever get. So what is the divergence test? So divergence test is very simple. Sum of an, infinite sum, right, of an, diverges if limit n goes to infinity of an is different than 0. That's all we need to know. It doesn't work the other way. So this is it. If the limit is 0, we don't know. Could diverge, could converge. We'll see that. But if the limit is different than 0, then it guarantees divergence. That's what's called divergence test. It's only used to detect divergence. This test can only detect divergence. That's it. This test cannot detect convergence. It's called divergence test. So clearly, it's for divergence only. The way it works is very simple. Summation of 3n plus 1 from 1 to infinity. Right, converge or diverge? Well, limit n goes to infinity of 3n plus 1 is infinity, which is different than 0, divergence by divergence test. It's that simple. Summation 1 to infinity of 4n squared plus n minus 1 divided by 2n squared plus 3. You immediately go limit, n goes to infinity, 4n squared plus n minus 1 divided by 2n squared plus 3 is equal to 4 over 2, which is 2, different than 0, divergence. If your limit is anything other than 0, the problem diverges. The series diverges. Summation 1 to infinity of 1 over n, limit n goes to infinity of 1 over n is 0. I have to write this in blood. Test is inconclusive. That means we don't know. This test did not give us different than 0. So this problem can still converge or diverge. This test is not working here. So summation 1 over n can still converge or diverge. We need different test. Test is inconclusive because it didn't give us a value different than 0. It gave us equal to 0. So test is useless for this problem. We cannot use it. We cannot use it. So that is the divergence test. You have to learn this one statement. So if the limit of an, which is the sequence inside the series, if the limit of the sequence is different than 0, then series will diverge. That's it. That's the only statement. Now, if the limit is 0, then all bets are off. We don't know. We have to use a different test. That's that. Next test, integral test. And this is a long test. Long calculations. Let's see if we can make it. For integral test, you need to check and prove that the three conditions that you have to work out before you set up and do integral test. So integral test is a two-step procedure. So it's a two-step procedure. Number one, check three conditions. All three have to hold. Then, I don't want to put these ones actually. Then we can move to stage 2. This is stage 2 over here, or step 2. Two-stage procedure, huh? Two-stage procedure, I guess. Then we can move now conditions. Number 1, f of x is decreasing. Number 2, f of x is positive. And number 3, f of x is continuous. So if all of this holds, and you will do 3 proofs for those 3 bullet points at the bottom. If this holds, then stage 2 kicks in. Summation from a to infinity. A, now I don't want to use a, let's use b. Will be converted into the integral b to infinity of f of x dx, and then you use what you learned, right, which is technically your exam for this weekend. You use what you learned for improper integrals. Solve improper integral. And this is in a stage 2, conclusions. Number 1. Oh, no, sorry. Let's do it this way. Maybe capitals? Both series and integral converge, or both diverge. So it looks like, well, it is a lot. It is a lot. But it's very structured. We check the 3 conditions on f of x, and f of x is literally your an, except in n's you have x's. So we are creating a continuous function, f of x, out of the discrete function an. So once we have a continuous function f of x, we check the 3 conditions, make sure it's continuous, sure it's positive and decreasing. And then, if those 3 conditions hold, we can use the converted function inside the integral. Series converge if integral converge, and series diverge if integral diverge. Very, very simple. Let's check that out on an example we just had. Summation 1 to infinity of 1 over n. So my an is 1 over n, which means that the f of x is going to be 1 over x. So we now have 1 over x as our function. Now we need to check the 3 conditions. Now those are the proofs that we have to do to make sure that this holds. You can do them in any order, and if you are able to use a graph on exam, you can't use a graph unless you know what the graph is. You either know to graph or it's included in the problem. But in general, you can also sometimes look at the graph and come up with some of these. So let's go with, I guess, positive first. Whatever. What did I list? Decreasing. All right, decreasing. Is it decreasing? Well, it's sufficient for me to draw the graph because the graph clearly shows that it's decreasing. The function is decreasing. Used graph, because we are getting a big fat green check mark there. Used graph. You can clearly see it's decreasing. One over x is decreasing on the entire domain. Why did I use the word entire? Because very soon we're going to just look at the part of it. Number 2, positive. Word positive means above x-axis, so your y's all need to be positive. We can draw the graph. It's the same graph as before, right? And you might say, well, no, it's not positive because this part is below x-axis, that part is negative. Yeah, but we don't care about that part. We only care about 1 onward. Why do I care about 1? Because we start at 1. When I draw my integral later on, it will start at 1. So we don't care what happened before. So yeah, I understand that there's a whole piece of a function that it's below x-axis, making it negative y, but we don't need that part because we are on the interval from 1 to positive infinity. So we are only looking at this. And are all of the values in there positive? The answer is yes. Every x from 1 to positive infinity, right, will give you positive terms. So 1, I need to be dramatic, 1 over x on 1 to infinity is positive. Word positive means above x-axis. And please note that I only looked at this part here. I did not care what happened before that. We're only looking at the small, right? So now that's our positive. And finally, we have continuous. Now, this is the part where you invoke those theorems you all learned in Calc 1. There is a theorem which says that polynomials are always continuous. So, 1 and x are continuous on negative infinity to positive infinity. Now, 1 over x is not continuous at x equals 0, but we don't care. because our interval is 1 to infinity. It doesn't include that 0. Is not continuous at x equals 0. But we don't care about x equals 0 because the domain is 1 to infinity. Why is it 1 to infinity? Because we had summation start at 1 to infinity, and then integral will be 1 to infinity as well. So we have to just be careful, right, what values we're using. So 1 over x is not continuous. Now, something like this you would not be actually writing in a proof because it's not needed, right? I wrote it out because I am explaining, right? I'm going to get rid of it now, and we're going to write what needs to be written there. So 1 over x, 1 and x, they're both continuous functions on negative infinity to positive infinity. Now 1 over x is not continuous. So now I'm going to change this wording, and I'm going to just say it. 1 over x is continuous on 1 to infinity, right? It's not continuous at 0, but it's continuous right after that 0. So continuity is okay as well, because the function 1 over x is continuous from 1 to infinity. Now we know it's discontinuous at 0, but that's not in our domain, so we don't care about it. Now all three conditions are satisfied. That means that I can convert my summation of 1 over n from 1 to infinity into the improper integral 1 to infinity 1 over x dx. So we're able to convert this into my problems, and now we know what to do. Limit b goes to infinity, integral of 1 to b, and you can put this x to the minus 1 dx if it makes you happy. Make sure you copy the limit every line, every step until you are ready to use it, because you might forget. Integral of x to the minus 1. Oh, I should have left it at 1. 1 over x. We all know what that is. What is integral 1 over x? Very good. ln absolute x. And that's calculated from 1 to b. So I have limit b goes to infinity of ln of b minus ln of 1. Now ln of 1 is 0. So that leaves us only with ln b. But that's infinity right there. Right now this one is going to shoot to infinity. And that is divergence. So divergence. Now that's not, I mean, that is the answer to our question, but you need to write the whole answer. Since all three conditions hold and integral 1 to infinity 1 over x dx diverges, the series summation 1 to infinity 1 over n diverges by integral test. This is your answer to the question. It's very structured. It's very long, yes, but it's very structured. You check the three conditions, you convert the summation into integral. You solve the improper integral. You learned that in chapter 8. And then you have the answer, since all three conditions hold, and the integral of 1 to infinity of 1 over x dx diverges. Right, since those two are there, the series 1 over n will diverge by integral test. So there is this correspondence between the two worlds, right? The world of So this is what you this is what you get. You have to balance it out, right? There's a world of conditions you have to compute. There's a integral, right, that you have to do. What's important at the end is if the integral converges, your series is convergent. If the integral diverges, the series will diverge as well. Let's take a look at another example, obviously. And that example is going to be similar, actually. Check for convergent divergence. 1 over n. 1 over n squared. 1 over n squared. Right? So how is this possibly going to be any more complicated or anything like the previous one? It won't. It's the same amount of work. Now, why we're doing it, that's a completely different story. So my an now is 1 over n squared, which gives me that my f of x is 1 over x squared. Okay, I have that. The next order of business is to do the 3 proofs regarding my f of x. Number 1, positive. No, I did decreasing first, right? There are 3 ways in which you can find that the function is decreasing to do the proof. So 3 ways. Pick one of the 3. Maybe sometimes you can do one of them. One way is to graph and look. Obviously not good for exams which have no calculator. I know we are in a special situation now, but right, graph and look, maybe you don't know how to graph this basic function. So that's one. Another one, to figure out that something is decreasing, is to simply find the first derivative. Actually, I should just write first derivative test. You might remember that one from your Calculus 1. First derivative test. What does it show? It shows increase and decrease. You are looking for decrease, right? And the third method is comparing terms in AN. And obviously that means that the next term, which is an plus 1, needs to be smaller than an. That's how you get decreasing. Right? If the next term is always smaller than the previous one. Pick one of the methods and do it, right? For 1 over x. So if you want to use the graph, you look at the graph, 1 over x looks like this, and you see that, is it decreasing? Yes, it is decreasing, because again, we're looking for 1 to infinity. We are looking only over here. Because the 1 on the left is increasing, but it's not in our domain. Our domain is 1 to infinity. So yes, on 1 to infinity. That's all we care about. You can also do the first derivative test. That's also possible. What is the first derivative of that one? Negative 2 over x cubed. Right, that's your f prime of x. So we have a vertical asymptote, and function is not differentiable at 0. Vertical asymptote is at x equals 0. So why do I need to know that? Because I need to do my partitions, if you remember your values. And now what do we have? We have test points. And we can say that f prime of -1 is -2 over -1, which is +2. That's increase. So we don't want that side. And f prime of 1 is 2 over 1. Sorry, -2 over 1, which is going to give me -2, which is a decrease. So this method told me that there is a decrease over -1. So these are the three methods. Oh no, these are the first two methods to figure out whether it's decreasing. So we had the graphical approach, or you have the first derivative, or comparing two terms. So how much is your A0? No, A1. A1 is just 1. How much is A2? I plug 2 for n, so 1/4. How about A3? 1 over 3 squared is 9. So you see that the sequence is decreasing. 1/4 is smaller than 1 over 9. You can, well, let's put one more. Why not? We can. 1 over 16. Right? So the larger the denominator, the smaller the fraction. So we see it's decreasing. Now that's a very dangerous business to list values and then generalize from there. No. The only thing you need to learn are procedures and theorems. The rest, you just follow what you learned, right? Procedures and theorems. So I can use this formula here to see the pattern. Now this one is obviously easy. I mean, 1/4, and obviously it's getting smaller. But can we use the formula for that? And the answer is yeah. So what do I have? I'm trying to show that 1 over n squared plus 1, no, lies, a to the n plus 1, like that. That's this, and that needs to be smaller than an, which was 1 over n squared. Squared an. That's what I was. N plus 1 squared. There we go. Much better. So I have n plus 1 on this side, and I have n on this side. So now you just work out arithmetic and see if this holds. It needs to hold. If it holds, then we're good to go. If it doesn't hold, so this is all three different ways to show the same thing. So now when I cross multiply, I have n squared less than n squared minus 2n plus 1. Well, if I subtract n squared on both sides, I get 0 is less than something that has n in it. And yeah, that should be it. So we do show decrease, right? We do show decrease. Number 2, positive. So we can look at the graph, but we can also argue this way. 1 over n squared, or 1 over x squared, whatever one you had. You can say x squared is positive. That much is clear because it's squared. Any number squared is always a positive number. If you start with a negative, negative times negative is positive. If you start with positive, you have positive times positive is still positive. So x squared is positive. And then you compile that into 1 over x squared. And you say positive number divided by another positive number is going to give you a positive number. So yes, it is positive. Whatever way you like to do this, it's fine. And finally we get to continuous part. That's number 3. And this is the one that should be the freshest for everyone because it was just the last semester. Talking about the limits and domain and range and all that good stuff, right? So, is it continuous? Yeah, it is continuous because 1 and x squared are continuous on negative infinity to positive infinity, right? Both of those functions. Now, when you put them together using function multiplication and composite functions and all of that stuff, you will get 1 over x squared, where we know that this only doesn't work when it's 0 in denominator, but we don't care because we start in our domain at 1. So is it continuous? 1 over x is continuous on 1 to infinity. So you have to be very careful about these things, because right now we use the restricted domain to make a non-continuous function into a continuous function that has smaller pieces in it. Now that all 3 conditions hold, we can finally do the integral 1 to infinity 1 over x squared dx. As I hope the preparation for exams are going well, and you already know how to solve this in your sleep, because that's not a tough one. The other one is the tricky one. All right, this is the straightforward. You see, its top limit needs to be infinity, and this is x to the minus 2 dx. So this is limit b goes to infinity, and we take negative 2, we subtract 1, becomes negative 3. So this is negative 2x to the negative 3 from 1 to infinity. So what do we have? We have the limit. We didn't use it yet, so we have to copy it every time. Why did I put infinity with 3 loops? There we go. Well, this was supposed to say b. I have negative 2 over b cubed. Minus and minus will give me plus 2 over x cubed. So limit b goes to infinity, and now we plug in, well actually no, I don't need to, man, I can just compute now. What's that? Oh, this is x. There we go. Good. Alright, so now plug in the limits. Limit b goes to infinity. And we have what? Plug in b first, so negative 2 over b cubed. Why do I have this term? What's going on over here? Ah! I gotta take some water. Yep, I'm reading the chat. Thank you. Yes. I've been at this stuff since 11. Okay, so now in addition to checking which class I'm supposed to teach and which day it is when I wake up, I also have to check whether I integrated or differentiated. I'm supposed to integrate. The exponent goes up. Thank you. Yes, I'm losing my mind. All right, I'm just gonna reset for another 7 seconds here. Okay, so we did the 3 conditions. They all worked out. It's positive, decreasing, and continuous. We write our improper integral. We put our limit over here for the b value up there, and now we are ready to integrate. When you integrate, you have x to the minus 1 over minus 1 from 1 to b. There we go. So that is limit of negative 1 over x from 1 to b. If you could just do virtual clapping now, that would be just amazing, because I fixed it. I was quite completely lost. Alright, so now limit b goes to infinity. We plug in negative 1 over b plus 1 over 1. This puppy will go to 0, and the whole thing is 1, which is a convergent integral. And this means that the series will converge as well. So, since all 3 conditions hold, and integral 1 to infinity 1 over x squared dx is convergent, the series summation 1 to infinity 1 over n squared converges by integral test. This is your answer right here. This is your answer. Now, integral converges to 1. We have no clue what the series converges to. We just know it converges. Remember what I said the last class, right? 1.3 was very special because the only 2 methods that allow us to see, right, the tests, which allow us to see what the series converges to, are, right, those 2 tests. And the other tests, if the problem converges, we have no clue where it converges to. So we don't know what it converges to, what the sum of it is. That's what the word convergence means, right? It means the sum. So we don't know what all of the members add up to. We just know they add up to a finite number. Let's take one more problem for this. Oh, by the way, yeah, I'm going to actually do it now, and then we'll go back to integral test. So let's summarize this so we can get something nice. Summation 1 to infinity of 1 over n diverged. Summation 1 to infinity 1 over n squared converged. Now I'm going to tell you and save you some time, 1 to infinity 1 over n cubed will also converge. Summation 1 over n to the 4 will also converge. And you can do integral test for each one of these. You know, one by one. Exam question, let's say, right? You should be able to do it. Now, what I'm going to do now is define p-series. P-series summation 1 to infinity of 1 over n to the p. Do we all see that all of these are the same? Except the power is different. Power is 1, power is 2, power is 3, power is 4, right? We all see that? So that's your p value. So what do I have? If p is larger than 1, series converges. If p is less or equal than 1, series diverges. That's your p-series test. It's actually a special case of integral test. Do you need to know p-series? Well, it's really fast. You just look at the value of p and you know. But you can also use integral test to go through the long calculation every time you need something, right, in this section. So, an example over here would be summation of 1 over square root of n, 1 to infinity. Well, you look at the problem, you determine that p is a half, you know that's less than 1, which means divergence by p-series. Problem is done, guys. No calculations. You look at the value, just like you looked at r when you did geometric series. You look at the r and you know it falls where it's supposed to fall, it converges and so on. So now every p that it's bigger than 1, not equal, just bigger, right? Bigger than 1 will give you convergence. Anything that it's 1 or less will give you divergence. It's a very simple test. You just look at the value for p and you memorize the test. What happens for p bigger than 1 and what happens with the p smaller than, or equal than 1. So p-series was a little sidetrack, right, from the integral test. Now back to integral test. Back to integral test. More examples. We'll do one more example and then we're going to switch to... So one more example and then we're going to switch to review. Part 1. There will be a part 2 review on Thursday. And then exam on Friday, Saturday, Sunday. So I'm going to jump here and look for a question. Oh, that's a cute one. But not now. So problem 18 says 1 to infinity, 1 over 2k plus 4, they like the k, squared. All right. Integral test. I need to show 3 conditions. Then I need to do that integral. If the 3 conditions pass, I need to do the integral. And then write the conclusion and I'm done sometime next year. Let's see. So number 1, decreasing. The fastest way for me to check this is to actually take the derivative, right? Because my AK is 1 over 2k plus 4 squared, which gives me f of x 1 over 2x plus 4 squared. So is it decreasing? The fastest way is to find the derivative, f prime of x, and do the test point. Remember that we are on the interval 1 to infinity, right? We are on 1 to infinity. You have to keep that in mind because there's a 1 and there's infinity, right? So we don't care about any other values. All right, what's happening with f prime over here? Well, f prime, that's a derivative over there. It's going to be a negative 2x plus 4 to the negative, to the 1 when you take 1 away. No, that was negative 2. That was right, negative 3. Help me, guys. And then the derivative of the inside is 2. So the derivative ends up being negative 4 divided by 2x plus 4 cubed. Now, since x is bigger or equal than 1, that's what this means. F prime of x is always less than 0. Think about it. If all of these numbers are positive, your denominator is always positive, you will always have negative divided by a positive, and that always gives a negative number. So if the first derivative is negative, that means decrease. And we're done. The next one is the proof for positive. Again, you can do this in any order. So is this positive? Is f of x 1 over 2x plus 4 squared positive? The answer is big fat yes. Because we have positive number divided by another positive number, which gives us positive number. Why is that so? Well, 1 is just 1, that's a positive number. The denominator is squared. And anytime you square a number, you get a positive, right? Negative 3 squared is 9. 3 squared is 9. So no matter what you square, you always end up with a positive value. So, positive divided by positive is positive, and we get the big fat chat over there as well. And now, number 3, continuous. Now, those are the theorems from Calculus 1. And we have that 1 and 2x plus 4 are continuous on negative infinity to positive infinity. Again, we don't care for this much. We only want 1 to infinity, but we know that these two basic functions are continuous. Then, one of the theorems also said function composition of two continuous functions is continuous. Function composition of two or more continuous functions is continuous. What are my composite functions? I have 2x plus 4 and x squared. Because when you plug this one in, you get 2x plus 4 squared. So that's all squared away, right? You understand that part? So function composition is, right? So this is how we put those two together and claim the continuity on that one. And finally now, we can take a look at the continuity of the whole problem, making sure that the denominator is never 0. So if you have 1 over 2x plus 4 everything squared, right, as f of x, we know that 1 is continuous. We know that the whole denominator is continuous. So all I need to make sure that whatever is under the can be 0, right? So we just want to show that denominator cannot be 0. And it cannot be 0. What is the lowest value you plug in? The smallest value you plug in is x equals 1. And your denominator is 2 plus 4 equal to 6. You can't go lower than that. 6 is the lowest denominator that you can get, right? So it's impossible for denominator to be 0. And because denominator, well, actually you need to square it, so 36 is the 1 over 36. So there's no way for us to have a 0 in denominator, right? So this is all continuous on 1, 2 to 2. So we are able to come up with all of these. We can also say the quotient of two continuous functions is continuous function provided that denominator is not 0. We looked at the denominator, we know it can be 0, the lowest it can be is 36, and then it's just going to go from there. So what I know here is that the function is continuous on 1 to infinity, because you can't make 0, you can't break it in any way. So now that we have that, we can go 1 to infinity, and we have our dx over 2x plus 4 squared. That's going to give us limit. B goes to infinity. Let's see if I can do this one right. We have dx over, oh, the limits are 1 to b. There we go. And dx over 2x plus 4. We can use u sub. And that's going to be u equals 2x plus 4. And du equals to 2 dx. I don't have a 2, so I'll put in the 2. This half can escape the limit as well. You have to write limit in every step. I'm going to leave 1 and b limits. I'll be back into the x domain. So what do I get there? I get du over u squared, because the whole parenthesis on the bottom, and then 2 dx is du. Good. This is 1/2. Limit b goes to infinity, and now we have u to the minus 2, so that's going to be that negative 1 over x from 1 to b. That's 1/2. Limit b goes to infinity, and what do I have? Negative 1 over b plus 1 over 1. The whole thing is a half. Converges. So since all three conditions hold, and integral 1 to infinity of dx over 2x plus 4 squared converges the series summation 1 to infinity of, what was that? Where is it? There it is. So the summation 1 over 2, so they use the k's there, 1 over 2k plus 4 squared converges by integral test. So we had, this is it for the chapter, for section, right? Obviously we did have 3 tests, but you know, this integral test stands out as the messiest, right? The best test is obviously our divergence test that we had because it's fast and it can eliminate a couple of problems, right? When you start the exam, you just look which ones can be quickly worked out just by looking at the basic limit. And integral test, right? And its partner in crime, right? P-series, which is just a special case when you have some of the, like those powers when they line up nicely. We are going to use P-series and that theorem when we reach the comparison tests, because you will always be, not always, but most of the time, you'll be comparing it to some form of the P-series. And the P-series, you just memorize, when you memorize the rules, it's a joke, right? P is either bigger than 1 or smaller than 1. and that's your converge diverge. It's a very systematic thing if you memorize these tests. If you don't know, I know exactly what's going to happen. If you don't learn the tests, you don't memorize the tests, when you see stuff on a test, you'll try quickly to find the formulas and examples and so on, and then you're going to complain that you didn't have enough time. Yeah, you do not have time to search for answers and examples and things when it's the exam. You just have to go and do the exam, right? That's it. You research and learn before. All right, so let's restart this mess for the office, not the office hours, sorry, for the review.